We're taught that the constants of nature are fixed, the speed of light, the strength of electromagnetism, the numbers that set the scale of atoms, stars, and even galaxies. Physics treats them as fundamentals, values that simply are. But what if they aren't fixed at all? What if they come from somewhere? What if the reason C has the value it does isn't determined by relativity, but by the matter of the universe? What if inertia, time dilation, even E equals mc squared aren't built into space-time, but emerge from the cosmos itself? Because there is a theory that makes exactly that claim, and if it's right, it doesn't just tweak Einstein, it reframes the foundations and opens the doorway to a different way of thinking about the universe, where the laws of nature come from nature, where relativity is rebuilt from the top down, and where the standard lambda CDM picture, expansion, dark energy, primordial hot beginning, is not required at all. This is cosmic relativity, a theory that tries to explain the constants Einstein had to assume, and in doing so offers a radically different view of the universe. Ideas like this don't appear out of nowhere. Long before Einstein, Ernst Mach asked a deeper question. Why do objects resist acceleration? Why does a mass have inertia? Why does a gyroscope know what non-rotation means? And why do straight lines feel special? Mach believed inertia wasn't local, that every object in the universe might influence every other. Einstein was inspired by that idea, but general relativity never fully delivered on it. General relativity gives us curved space-time, but not the relational universe Mach imagined. The question never died. Sharma, Hoyle, Narlikar, Barber all tried to recover that missing link between the universe and local physics. Cosmic relativity is the latest chapter, an attempt to finish what Mach began, a picture where inertia, time dilation, even the speed of light aren't absolute truths, but consequences of the cosmos. Cosmic relativity wasn't written by an outsider. C.S. Unikrishna spent decades at the Tata Institute of Fundamental Research, one of India's top research centres. His work spans quantum optics, interferometry, gravitational physics, fundamental concepts, and high-precision measurements, fields that all circle the same question. What do our clocks, rulers, and detectors actually tell us about reality? And when you read through his papers, a pattern quickly emerges. He isn't just collecting results, he's probing the foundations of physics. Time, motion, simultaneity, reference frames. The quiet assumptions that usually hide underneath the equations. He's both experimentalist and philosopher. He builds instruments, then asks what the results mean. And that curiosity drives a question most physicists avoid. What anchors the laws of physics themselves? If clocks slow, if the speed of light is fixed, if inertia resists acceleration, then what sets those rules? Why those numbers and not others? Unikrishna believes the answer isn't in local geometry, but in the universe as a whole. Cosmic relativity is his attempt to rebuild that link. His idea sounds bold, but the structure of it is actually very simple. You can understand cosmic relativity through two main pillars, two ideas that do very different jobs, but together build the foundations of relativity. The first pillar begins with a straightforward observation. If matter fills the universe, then every point in space sits inside the combined gravitational potential of all that matter. You don't feel a force from it, the pull from distant regions cancels, but the potential doesn't cancel, it accumulates. It's a bit like standing inside a hollow sphere. No force, but a definitive potential. Cosmic relativity takes this seriously. It argues that this cosmic gravitational background isn't just a mathematical curiosity. It quietly determines the values of the constants we treat as fundamental. In this picture, the laws of physics don't float free, they're anchored to the mass distribution of the universe. Nature makes the rules because of the matter nature contains. That is the first pillar. The second pillar answers a different question. If the universe sets the laws, how do we actually measure those laws? Here, cosmic relativity points to something we already know. The cosmic microwave background has a clear rest frame. The tiny dipole pattern in its temperatures tells us exactly how fast we're moving. In standard relativity, this is treated as a coordinate convenience. In cosmic relativity, it becomes the physical rest frame of the universe, the place where the cosmic background potential is seen in its undistorted form. Only observers at rest relative to the CMB measure the true value of C. Anyone moving through the background sees their clocks, rulers, and even their synchronization procedures shift. Those shifts completely mask any directional dependence in all two-way light speed measurements, which is why every ordinary experiment from Michelson-Morley to modern interferometers still return the same value of C. But here cosmic relativity makes a claim that special relativity forbids. It argues that certain directional, phase-based single clock measurements, the kind that do not rely on synchronizing distant clocks, can pick up a tiny dependence on the laboratory's motion through the universe. Not a simple one-way time experiment, which always yields C, but a class of one-directional processes where phase evolution itself is sensitive to the absolute velocity. This is the key difference. Special relativity says no experiment can reveal uniform motion. Cosmic relativity says a specific kind of one-directional phase-evolving measurement can. Individually, the two pillars look separate, but together they define the logic of the entire theory. The first pillar anchors the laws of physics to the universe, to its matter, its structure, its gravitational background. The second pillar anchors our measurements to a specific frame inside that universe, the rest frame picked out by the CMB. One pillar explains the origin of the rules, the other explains why those rules appear the way they do to observers in different states of motion. Once you take the two pillars seriously, relativity stops looking like a theory we know. The maths can resemble Einstein's, but the meaning underneath changes. Special relativity begins with a simple axiom. All observers measure the same speed of light. Everything else, Lorenz's symmetry, time dilation, length contraction, follow from that assumption. Cosmic relativity keeps the observations, but changes the origin of the symmetry. Instead of the geometry enforcing a constant c, cosmic relativity says the universe itself enforces it. Light has a true, universal speed only in the cosmic rest frame, and observers moving through the universe see their clocks and rulers physically change just enough to keep their measurements of c unchanged. Special relativity says c is constant, so clocks slow down. Cosmic relativity says clocks slow, so c appears constant. The equations look similar, the cause is completely different. That single reversal reshapes everything that follows. In special relativity, time dilation is a geometric effect. Two observers in uniform motion each see the other's clock running slow, because special relativity treats all inertial frames as physically equivalent. No frame can claim to be at rest, and no clock can claim to be running normally. Everything depends on the relative velocity and nothing else. This is what leads to the famous twin paradox, but only in the way it's usually presented. In the textbook version, one twin accelerates, turns around and comes back younger. But as soon as one twin accelerates, the situation is no longer symmetric, so special relativity has no contradiction to resolve. Acceleration doesn't explain the aging difference, it simply removes the requirement that special relativity treat two frames equally. Once the symmetry is gone, special relativity can integrate the world lines and the result follows. The real paradox appears when both observers remain inertial. Imagine stripping the universe away entirely, no stars, no planets, no external reference frames, just two identical twins drifting past each other in deep, empty space. Each sees the other moving, each predicts the other's clock is running slow, and because all inertial frames are equivalent, special relativity has no physical rule that says who is actually going to age less. No experiment can break the symmetry, and special relativity forbids any preferred frame that could. You can compute proper time once you pick a frame, but special relativity provides no physical reason to pick one frame over another. The paradox never really disappears, it's simply hidden inside the geometry. Cosmic relativity removes the paradox entirely. The symmetry was never real. Time dilation is a physical effect caused by motion through the universe's gravitational background. One twin is always closer to the cosmic rest frame. The other always moves faster relative to it. The twin near the cosmic frame ticks faster. The one moving through the background ticks slower. The asymmetry is physical, not geometric, and the explanation does not depend on acceleration or who changed frames. It depends on motion relative to the universe itself. Special relativity reproduces the numerical result. Cosmic relativity explains it. Special relativity elevates all inertial frames to perfect equivalence. No experiment can reveal uniform motion. Cosmic relativity rejects that. It preserves the appearance of symmetry in everyday tests, but says that beneath that appearance, one frame is special, the one in which the universe is at rest. The cosmic rest frame becomes the reference against which clock rates, simultaneity, and motion ultimately acquire meaning. You still measure c in every direction, but the frames themselves are not equal in principle. This is the deepest break with special relativity. If c is set by the universe, then everything built on c inherits that dependence. In Einstein's special relativity, E equals mc squared is enforced by Lorentz's symmetry. It tells us mass has energy, but not why that energy exists or what sets its scale. Cosmic relativity keeps the symmetry, but gives it cause. The same equation becomes a statement about how mass couples to the gravitational potential of the universe. Special relativity treats inertia as a given. It never explains where resistance to acceleration comes from. Cosmic relativity says inertia has a cause, the universe itself. In that view, the constants of nature aren't features of empty space-time, they're the signature of the cosmos that sets them. In general relativity, the geometry space-time is flexible. If you apply Einstein's equations to a universe that is smooth on large scales, the most general solution is one where the geometry itself changes over time. Space doesn't sit still, it expands or contracts. That's where the cosmological scale factor comes from, and why modern cosmology begins with an expanding background. But that global behaviour is separate from the local predictions of general relativity. The way clocks tick near Earth, the bending of light near a star, the gravitational redshift between two heights. None of those depend on cosmic expansion. They follow from a local curvature, and cosmic relativity keeps all of that intact. What cosmic relativity removes is the assumption that this large-scale geometry must evolve. If time dilation and inertia come from motion through the universe's gravitational background, then you don't need a stretching metric. The universe provides the reference, the background potential provides the physics, and the large-scale geometry doesn't need to expand. Locally, relativity behaves exactly as general relativity predicts. Globally, expansion is no longer the starting point. And this is where the questions begin, because removing expansion removes the framework that modern cosmology depends on. Cosmic relativity gives us a striking reinterpretation of motion, clocks, and the meaning of the speed of light. But the first open question appears long before we even reach cosmology. It starts with something simpler: how we predict the behaviour of a clock. In general relativity, time dilation comes straight from geometry. You write down the metric, add the gravitational term and the velocity term, and the equations tell you exactly how fast a clock will run. Cosmic relativity keeps the prediction, but replaces the geometric explanation with a cosmic one. Motion through the universe slows physical processes. The problem is that the theory hasn't yet written down how that slowing is calculated. To compare an Earth clock and a satellite clock, you would need to compare both to the cosmic rest frame. And cosmic relativity hasn't yet spelled out the rules that link that motion to the actual ticking of a physical clock. So the numbers survive, but the machinery behind them is still unfinished. A similar gap opens the moment you look at redshift. Without expansion, photons aren't stretched by a growing scale factor. And with a steady cosmic background, they don't accumulate gravitational redshift either. So something else has to drain the energy from the light as it travels. Some kind of tide-like mechanism becomes unavoidable. Cosmic relativity hints at an interaction with the cosmic potential, or perhaps with the CMB itself. But it doesn't yet describe the physics behind that process or a distance redshift law that could be tested. The same issue appears when you turn to the CMB. If the universe never had a hot beginning, the CMB can't be a fossil from the early plasma. In cosmic relativity, it becomes a present-day, steady-state radiation field. That idea is conceptually elegant. A stable universe could in principle maintain a background temperature. But the obstacle isn't the temperature, it's the structure. The CMB's acoustic peaks look like frozen sound waves from a primordial plasma. If they aren't relics, they must be generated and sustained. And cosmic relativity hasn't yet shown what process could produce those harmonics, or why they sit at the angles we observe. Then there's the problem of the light elements. In a universe without a hot beginning, hydrogen and helium aren't fixed in one early burst. They have to be replenished, but stars burn hydrogen into heavier elements. Supernovae push the material up the periodic table. Over long timescales, the light element should gradually disappear unless some process restores them. Cosmic relativity doesn't describe such a mechanism. Other ideas exist, plasma-based synthesis, low-energy nuclear reactions, but they come from outside the theory, not from the theory itself. And finally there's structure. In lambda CDM, the cosmic web grows from tiny early fluctuations, slowly amplified in an expanding background. Remove expansion, remove the early hot phase, and that entire growth mechanism vanishes. A static universe would need a completely different engine. Gravitational, electromagnetic, or plasma-based to organize matter into filaments, sheets, clusters, and galaxies, and to keep that structure stable over cosmic time. Cosmic relativity doesn't yet provide that engine. It reframes relativity, but it doesn't yet describe how the universe acquires the structure we actually see. None of that means the theory is wrong. It simply means the foundations are in place, but the higher floors of the building haven't yet been constructed. Cosmic relativity isn't a polished alternative. It isn't finished, and in a sense, it doesn't have to be. It's a doorway, a reminder that the laws we treat as fundamental might not be fundamental at all. They might be expressions of the universe itself, the matter it contains, the structure it holds, the background it provides. But beyond that doorway, the questions multiply. Redshift, the CMB, structure, the elements, all the machinery of cosmology waiting for new explanations. And that's where the script of history becomes all too familiar. Because every major idea in physics began this way. Not as a final answer, but as a fragment, a clue, a sketch of something larger. And when we step back, we see that cosmic relativity is one fragment among many. Tired light mechanisms, plasma cosmology, alternative nuclear synthesis, scattered pieces of an unfinished mosaic. None are complete. They all have holes, missing pieces, but that doesn't mean that they are worthless. Far from it. Together, they form the outline of a landscape we haven't yet explored. Maybe cosmology doesn't need another monolith. Maybe instead it needs pattern recognition, the willingness to assemble fragments and see what they add up to.